Hi, I am Ah Shin. Today we're going to introduce CAN bus.
It's used for communication within cars. This is because there are so many devices installed in the car. They need to communicate with each other for the car to function properly. If every device required a separate communication line, then there could be a multitude of cables. To simplify wiring, we can use CAN bus for communication. This allows all devices to share a single communication line pair. Today I will measure the CAN bus waveform in the car. Believe it or not, I even bought a car for this episode. My old car doesn't have a CAN bus. For my sincerity, you must watch this episode until the end. Since CAN bus is utilized in high-noise environments like cars.
When it was initially designed,
It adopted the differential signal format method. It contains two lines. One is named CAN high, the other is CAN low.
the waveforms of those two lines will be opposite to each other.
The signal is between two lines.
To observe the signal,
Simply subtract the two signals to obtain it. Even if there is interference, because the two lines are close to each other, the interference is identical. Subtracting the signals reduces the noise. Ultimately, only the signal remains.
this is the benefit of differential signals.
What should we do if data has been damaged?
Don't worry, CAN bus has its own error detection mechanism.
This implies that the transmitter will calculate CRC based on the sent data. This will be sent out along with the data. At this point, the receiver will recalculate the received data's CRC. It checks if the received CRC matches calculation. Data is discarded if they don't match. That's how the process works. Since all the equipment in the car is connected to the CAN bus,
Here you will find all the information about the car.
that's why you will see the technician connect the instrument to the CAN bus during maintenance to see which part is malfunctioning. We're actually going to examine the waveform of the CAN bus. I'll use this particular scope, GDS3652A. It's capable of decoding CAN bus signals. It can decode other protocol types as well. For example, RS-232, UART, I2C. However, today our focus will solely be on CAN bus. Before getting in the car, I'll let everyone examine the CAN bus waveform in the lab, because theoretically, there will be less interference indoors. The waveform will appear smoother to observe. The signal source I utilize is specifically this Arduino development board. Then we must use this CAN bus shield subboard. Now it becomes a CAN bus device. With this device we can determine what type of CAN bus data packet to transmit or receive.
This is the standard CAN bus packet format.
The ID is the unique number given to each device. Here I assume my ID is 0x123, or we say hex 123. The data I plan to transmit is set as AA, BBCC. Since the chip calculates CRC value, we don't need to do it. It uses CRC17, which is different from CRC algorithm in PC industry. These two terminals of this CAN bus shield are the two signal lines of the CAN bus. One is CAN high, the other one is CAN low. So I will connect the oscilloscope's channel 1 and channel 2 to these two terminals respectively. The probe needs to be connected to ground, right? Where should ground connect? Just connect it here. Here is a ground, right?
I've already taken steps to extend this particular ground pin.
I will connect the oscilloscope ground right here. Next, we'll see the CAN bus signal waveform. All wires are well connected. The oscilloscope is set to 2 traces. Simplicity is better so you can understand what I am doing. I have set the trigger level to approximately 3 volts for optimal performance. This is because the signal of CAN high is roughly between 2 volts and 4 volts.
Now, let's connect the DC power plug.
Once the power is on, the program runs.
I've modified the program using sample code.
Alright, we already have a signal here. CAN high, low. We slightly overlap these two distinct signals together. You can observe that CAN high is likely to be above 2.5 volts. Whereas CAN low is under 2.5 volts. That's a fundamental concept. Look at this. This is the CAN bus waveform and it is smooth, right? Now we need to decode this waveform. We'll extract the ID and data from the waveform.
We just need to press this purple button labeled bus.
Then, we select CAN, which we have previously chosen. We select CAN. After selecting CAN bus, you can clearly see here that we already have some data that has been decoded. Here is the ID 123 and the data we just wrote. The display appears to flicker. This is due to the trigger. The trigger level.
Now, I am switching over to the trigger menu interface.
Currently the trigger type is set to edge trigger. Edge triggering conditions can be satisfied by numerous different edges in various circumstances. So it appears to flicker due to different time shifts.
I am going to change the existing trigger condition
to the item named Others.
Press Bus button. We are going to use Bus function.
The bus item is the same as this button, since we are using CAN bus. So the trigger conditions here are all about the CAN bus. When is it supposed to be triggered? It is triggered when an identifier appears. It just triggers when every ID appears. You will see that the ID has now become our trigger condition. As soon as the ID appears, then the scope generates a trigger signal in the middle of this screen like this. If you need to trigger at a specific identifier value as you want, choose this one. And here a menu appears identifier. Then here you can fill in the value you want. Then it will trigger on this specified value. I have just one ID. I don't require specifying a particular value. Everything is XXX here. It is don't care condition. In this manner it can fulfill my needs. So let's examine this now. Is the content identical to our programming? Notice, our ID is 123, right? It matches what we set in the program. What about the transmitted data? We recently set A, B, B, C, C, right? So it aligns with the program settings we just inputted. Since the dataset consists of bytes, there are 3 bytes of data. Hence the data length here is 3. Therefore, the entire dataset is indeed correct. There is a CRC at the end. This CRC was not verified just now, but I believe it's correct. It's certainly beneficial to have an oscilloscope for decoding, but if you attempt to decode with only your brain, you must be careful. The byte data transmitted on the CAN bus may differ from your expectations. For example, the ID 555. Then this waveform appears normal as expected. However, if your ID is 000, the waveform is not a straight line. Why are 2 distinct bits noticeably dipping in the center? This is due to a rule in the CAN bus. If there are 5 consecutive identical bits, a bit of the opposite phase must be inserted after the 5th bit. This is a stuffing bit. If this stuffing bit and the subsequent 4 bits happen to exhibit the same continuous state for 5 times, then we must once insert a reverse bit at the end again. And so on and so forth. Why is this so? Because, between the transmitter and receiver of the CAN bus, there is no independent clock for synchronization. They can only synchronize through data changes. Hence the data cannot remain unchanged for a long time. Otherwise, the receiver will be unable to determine if the signal is faulty, or if it is indeed a continuous signal. Thus it needs to reverse phase periodically. Thus the receiver can synchronize with the transmitter. That's essentially what CAN bus is all about. This waveform was generated in the laboratory environment. It is incredibly clean. Look, this square wave is as it should be. The square wave is accurate. But in the actual car, can it maintain this cleanliness? What will the final appearance be? Let's test it directly in a moment. Currently the CAN bus interface of cars primarily utilizes OBD2. Thus I bought an OBD2 plug. Naturally this end is inserted into the car. On the opposite side, what I have recently acquired is indeed open-ended. I need to solder the wires, as it's the sole method to extract the signal from pin header. Let's see pin 4. It's the car chassis. Pin 6 and 14 are CAN high and CAN low. In this manner we can employ the scope probe to connect. Let's examine the actual car. The standard OBD2 is usually under the steering wheel. As you can see, it's right here. Let's lift this cover and have a look.
Wow, okay.
What's this? Shouldn't this be a cover? Why are there pins inside? So what exactly is this? Could you possibly tell me if it is a lid or could it be a signal wire? Is it appropriate for me to connect the oscilloscope probe directly to the purple connector? Or should it be attached to this black connector in my hand? To avoid damaging the car's OBD2 circuit, I bought an OBD2 splitter cable. This maintains the integrity of the entire OBD system in the car. And I can tap out the OBD2 signal. Can you see it? It links to the cable I assembled. We have a pin header located at the end of the cable. I can easily attach these oscilloscope probes to the pin header right here. You can see these probes and pin header. Oh, I noticed I inserted the probes into the wrong scope connector. I'll fix this later. Here is probe connection. Pin 1, 2, 3. Pin 6 is CAN high. 6, 7, 8, 9. Next 14. Pin 14 is CAN low. CAN high and CAN low. To attach the probe, a reference potential ground is required. The reference potential is linked to the chassis at pin 4. This represents the car frame. Some individuals suggest that pin 5, the signal ground, can also be connected. It's true. It's said that the ground at pin 5 has less noise. I haven't conducted a thorough study. Regardless, I believe both pin 4 and pin 5 can be connected. Now let's examine the CAN bus waveform appearance. But the engine hasn't even started yet. Why would a waveform be present? I don't understand this either. Let's start the engine. Alright. Upon starting the engine, we should see a signal, right? Yes, indeed, we can see it. What you see now is a more stable signal. A continuous waveform is consistently appearing. Let's examine the bus. Firstly, let's inspect the BU rate settings. The BU rate is set at. The data rate is currently 500 kilobits per second in this system. Let's examine its waveform. This is data, right? It seems to start with the number 7. Regarding the waveform, any interference here? Check it. Zoom in. Check detail. The waveform appears better than what I think. I assumed there would be some noise, but there isn't. There are only some burrs that are noticeably appearing at both the top and the bottom edges of the waveform. Essentially, this waveform, to me, is fairly clean. I believe it's quite clean. Regarding the burr, I believe the burr at this level is acceptable. Let's check the data. The data in the yellow field is the ID. It begins with 7. So this ID, in reality, it's a device located within the car to identify which is the engine speed, or which one is perhaps related to brakes or wheel speed? Well, I'm unsure. I've attempted to search the CAN ID list. However, I couldn't locate it. The manufacturer seems to hide the list from consumers. All vehicles must return for upkeep. Essentially, if you possess the ID, you might be able to hack into the car to modify settings. Altering settings could cause side effects. Who knows? Essentially, it is better to return for factory maintenance, unless you're familiar with this CAN bus system. Today I demonstrated the actual CAN bus waveform inside a car, just for satisfying curiosity. That's all for today. Don't forget to subscribe to Strong Pi Lab. Goodbye.